topic, you could say first real topic of this morning, or first new topic, I should say. The other two are definitely real topics. It's a single slide. It's a single slide topic that covers something that we could spend a few lectures on. But due to limited space in the course, we use only this slide. It is related to my comment about the two errors we can make in hypothesis testing. How can we do any better in hypothesis testing? Well, I was a bit critical towards using 1 out of 20, that is a 5% risk level for this very important alpha level. Why should we claim a new drug or a new cancer treatment or a new something in society is important with a 5% risk? It's a very high risk of making mistakes. Well, of course, we could make it smaller. We would be inclined to make this risk smaller. The problem is, if you make the alpha risk smaller, so instead of 5%, let's say 1 per mil, 1 out of 1,000 risk, it's a much nicer risk in a way to work with than I don't do a risk. But what is the consequence? The consequence is that I more often accept, right? If I make it more difficult to reject, I make it more easy to accept. Making it more easy to accept, I will, when I decrease alpha, I will increase beta. No free lunches here. Alpha and beta risks are a trade-off, right? If I want to have lower alpha risk, I will increase my beta risk. So it's a matter of trade-off between those two risks before I do my experiments. I cannot, well, there is one way, but that's the expensive way. We can increase the size of the experiment. The only way to improve both alpha and beta, that is, decrease both of them at the same time, would be at a higher cost. Increase n, that is, spend more money, right? We have a name for this type 2 risk, or rather, the positive version of the type 2 risk. Namely, not the risk or the probability of not finding something which is there, that's a type 2 risk. The risk that we cannot find something that we should find, we put it the other way around and call it the power. The power is the chance of actually finding something which is there. The power is the chance of detecting that a treatment is better than another treatment, assuming that it is. I mean, assuming that there is something to find, what is the chance that we can find it? That's the power. It can be computed if we speculate. That is something you need to do scenario-based. What if the truth is like this? Would I then find it by my experiment? Having the power, expressing the power, saying, I want to be able, let's say that a cancer treatment, let's speculate that a cancer treatment would save 10% more people. So you have a 10% higher survival rate among people who get this treatment compared to another treatment, like a 5-year survival rate, if that's what you're looking at. Then I would, that you could speculate, you want to test a new treatment, then you would have to say, how big an experiment, or rather, I should say, what is the chance, given 100 patients, what would the chance be that I would find such a 10% improvement? That's a good probability to be able to calculate, because if I realize that in an experiment with 100 patients, there is only a 40% chance that I will ever find this improvement, don't do this experiment. That's a waste of money, right? Either don't do the experiment or spend more money doing it. That's the only two sensible solutions. There is no sense in doing experiments that have no chance of finding relevant things out there, right? Don't do them. It's a waste of money. There are a lot of experiments like that being done because you don't know what's out there. So sometimes you just start doing experiments, but you should be clever about it. You should base some scenarios. You should make some scenarios on yourself and think about, does it really pay off to do this experiment? And here is one classical formula. There are many of such formulas and such computations out there. Here is the most classical one. If you speculate that your mu1, let's say that the one treatment is mu0, another treatment is mu1. Let's speculate there is such an effect, some effect, and let's speculate that I know the noise in the system. I have decided the type 1 error and the type 2 error. I've decided with which power should I be able to find, with which probability should I be able to find such a treatment effect. Then I can find n due to this formula. This formula I prove in a 14 minutes extra math video that you can go click yourself. You can actually find this formula given normal distribution calculations that you have been taught. I'm not going to spend the 15 minutes doing it here. You can pursue it yourself if you want. You can do it. It's not rocket science. It's just keeping your tongue straight in your mouth and using some normal distribution computations. So it can be done. You can speculate. You can find out what is the cost. N is the cost in price, number of people, patients. That's the size of the experiment. You can find out with some scenario thinking. It's not an easy task in a practical framework, but you can do it. PhD students, medical PhD students at Aarhus University, I think I mentioned this before, cannot be signed in as PhD students without thoughts of this type, thinking about what can you find with what you think you're going to do, what can it do for you. You are forced to do thoughts like this in many other contexts also, before you start doing it. That's where you should think about the trade-off between type 1 and type 2 error. What is the chance of finding something? How large should the investment be to actually be able to find it? This is as far as I will discuss power and sample size in our course. It's a very important topic, but we'll leave it at that. It's a topic that is, when you do experimentation and planning, it's part of the planning phase, right? The power and sample size, thinking and consideration is part of the planning phase of experiments. You could say all the rest of the course that I give you is part of the analysis phase. How do I look at the data and conclude when the data is there? Someone, either myself or someone else, did the experiment. Now I have to conclude based on what is there. That's another story. And that is most of our course. You can discuss whether that's the right weighting of things, but I think in order to be able to be intelligent about how to plan the experiment, you need to know the tools that you want to use to analyze. That's the thing. So you need to know these tools, and then you have to go back and think about the planning phase in a way after you know about the analysis tools. That's how it works in practice. And then we have a full course actually at our university, which is called Design of Experiment, which is thinking of some of these things and also other more complicated planning things when you do planned experiments. Okay, that was the second part, the power and sample size part. Now